Okay, identifying unusual results with the range rule of thumb. Okay, we talked about the range rule of thumb some time ago. Remember, we said that the maximum value, maximum usual value, is going to be the mean plus 2 standard deviations, and the minimum usual value is the mean minus 2 standard deviations. So if this had to do with the number of cans of was it caffeine that's consumed daily, then we could figure out the typical values using this range rule of thumb. If this is the same range rule of thumb that we talked about a little while ago. Okay, the rare event rule for inferential statistics. Remember, we said that we consider an event to be unusual when it has a probability that's less than what? 0.05. Very good. Okay, so that's going to be our kind of guideline to say that something is usual or unusual when it's less than 0.05. Okay? All right, very good. Okay. What else do we have here? All right, so let's see what we have. In example 5, we found that for groups of 5 offspring generated from parents both having the green-yellow pair of genes, the mean number of peas with green pods is 3.8 and the standard deviation is 1. Use those results in the range rule of thumb to find the maximum and minimum usual values. Based on the results, determine whether it is unusual to generate 5 offspring peas and find that only one of them has a green pod. Okay, so they already gave us the mean, they gave us the standard deviation. So to get our maximum and minimum, we're going to look at mu plus or minus 2 sigma. They said mu was what? 3.8, and our standard deviation was 1. So typical values for the number of green pods when we have 5 offspring would be 3.8 minus 2, so that's 1.8, to 3.8 plus 2, which is what? 5.8, which isn't even really possible. But when we look at it in a practical sense, it's saying that it's not unusual for us to have 5 green pods. Okay, intuitively, when the percent or the probability of getting green is 0.75, would you agree that getting 5 green pods is not unusual? Okay, so that makes sense. So this would be our range from minimum to maximum typical number of pods. So based on the results, is it unusual to generate? I already answered the question. Is it unusual to generate 5 offspring peas and find that only one of them has a green pod? Is that usual or unusual? For one green pod. Unusual. It falls outside of our range. Okay, so it would be unusual. Okay, use probabilities to determine whether 1 is an unusually low number of peas with green pods when 5 offspring are generated from parents both having the green-yellow pair of genes. Okay, let's see what that's all about. Okay, in the textbook, let's go back a little bit. It says we have an unusually low number of successes it says X successes among N trials is unusually low if the probability of X or fewer successes is unlikely. Okay, so basically we would say that one success is unusual if 1 plus the probability of 0 is less than 0.05. Okay, 0.05 is our kind of criteria to say that that's unusual. So we would say 1 is unusual if everything 1 or below is less than 0.05. So when we look at the example, looking at our probabilities, let's see, did I go too far? Okay. Okay, here are the well, that's for the soda. Here we are for the pea pods. When I look at the probabilities for 1 and 0, they add up to 0.016, right? 1 or fewer. Okay, the probability for 1 or fewer is 0.016, which is less than what? 0.05. So we would say that to get one is an unusually low number of peas with green pods when 5 offsprings are generated. Okay, does that make sense? A little bit? Okay. The question again was, is 1 an unusually low number? And so what I do is I go back and I look at the probabilities. I look at the entire probabilities for 1 and 0. Okay, everything that's below 1. Okay, and so when I look at all of those that are below 1 plus 1, all of that's still less than 0.05. And so we would say, yes, it's unusual to get 1. Okay? All right, very good. Yes? Where I was writing? Okay. Right here. X successes among N trials is unusually low if the probability of X or fewer successes is unlikely. All right. I think we talked about all of that. Okay, based on information from the MRI network, some job applicants are required to have several interviews before a decision is made. The number of required interviews and the corresponding probabilities are 1 with probability 0.09, 2 probability 0.31, 3 0.37, 4, you see all the numbers there. Okay. Does the given information describe a probability distribution? Okay, what do we need to look at in order to answer that question? What's that? Okay, does it add up to 1? And of course we want to make sure each value is between 0 and 1. Okay, so do they add up to 1? 0.99. Okay, so that's close enough. Okay, assuming that there was some round off error. So the summation of P of X is approximately 0.99. Or I guess I should say it was equal to 0.99, which is approximately 1. So we're okay with that. And each value was between 0 and 1. Okay. Part B, assuming that a probability distribution is described, find its mean and standard deviation. So what would we do with this? Use our calculator. Okay, so let's do that one more time. Okay, on the calculator, I'm going to go to Stat, Edit, And I'll just start back over here at 1. Okay. So we had values from 0 to, actually from 1 to 6. I'll just delete that. Okay, and then my probabilities are 0.09, 0.31, 0.37, 0.12, 0.05, 0.05. Okay, and so we'll do stat, calc, one variable stats. I'm going to do second L1, comma, second L2. Okay, and so X bar is 2.9, or we could say 2.88. That's our average, and or our mean. And then the standard deviation is 1.2. Okay? All right, did we answer the question? Find the mean and the standard deviation. Okay, questions about that? Okay, very good. All right, D, use the range rule of thumb to identify the range of values for usual numbers of interviews. Okay, so again, to use the range rule of thumb, we're going to look at mu plus or minus 2 sigma. Okay, mu in this case is what? What was it? 2.9. Okay, and the standard deviation was 1.2. Okay, so we'll do 2.9 minus, that's 2.4, so that looks like 0.5. Okay, and then 2.9 plus 2.4, 5.3. Is that right? Okay, 0.5 to 5.3. So, you got to have some interview. Would you say that it's unusual for a person to go and have just one interview? No. Okay, because that falls within our range of usual numbers of things. Okay, and that was the next question. Is it unusual to have a decision after just one interview? Okay, well, based on this, we say no. If we go back and look at the probabilities, what was the probability for having exactly one interview? What was it? 0.09? Okay, so that's more than 0.05, right? So again, that'd be another way to say that one interview is not unusual. Okay, questions about that? Okay, excellent. All right, making great progress here. Talk about is expected value. And expected value really is just another name for the mean, except we tend to use the term expected value when we have games that you might play, like at the fair, or betting games, or at a casino, anything really kind of involving money. Often instead of saying the mean, you got excited about money. Anything involving money, we call that really expected value. So again, it's the long run average. We tend to write E of X. That's our symbol or notation for expected value. But it is still, it's just the mean. So it's the summation of X times P of X. That was our formula for expected value, or for the mean rather, which is the same thing as expected value. The trickier part of what we're going to do here is have to come up with the probability distribution. Before we can find the mean, we need to know what the probability distribution is, and we'll use some of the information that's given to us to help us figure it out. Okay, so it says you're considering placing a bet either on the number 7 in roulette or on the pass line in the dice game of craps at the Venetian Casino in Las Vegas. Okay, it costs $5 to play roulette. The prize for winning is $180. If you bet $5 on the number 7 in roulette, the probability of losing is 37 over 38, and the probability of winning is 1 over 38. Find your expected value if you bet 5 on the number 7 in roulette. Okay, so let's deal with that first. Okay, this is part A. So before I can calculate expected value, I need to come up with my probability distribution for this particular game. What do we have to have for a probability distribution? Two things in order to construct one. Okay, very good. We list the possible values and the probabilities associated with each one. Okay, and remember that X is going to be quantitative. Okay, but when we play this game, the first thing we probably think about is we're going to do what? Either win or lose, right? You're either going to win or you're going to lose. Well, those things are not quantitative, right? So now we need to take this and convert it into something that is quantitative. Okay, let's start with lose. If we lose, what's the value of that? $5. It's out of our pocket. And in fact, it's a negative $5. Okay? That's the value of a loss. We just lost $5. And the probability of that happening is what? 37 over 38. Okay? If we win, the value is what? 180, 175, right? 175, because we paid $5 to play the game. So don't forget, from your winnings, you need to subtract what you paid to play. Okay? And so the probability of that is 1 over 38. Now that we've got that, we can come up with our expected value. And in this case, just depending, it's almost just as easy to do it by hand. Remember, it's just the summation of x times p of x. So we're talking about 175 times 1 over 38 plus negative 5 times 37 over 38. Okay, so 175 minus 5 times 37. I got negative 0.26. Okay, negative 0.26. Okay, so first of all, what does that mean? Remember I said that the mean or the expected value is the long run average. So when we play, I feel like that's these are our winnings. Does that make sense? Negative 5 times 37 over 38, that's our loss. Okay. All right, according to this, the long run average is basically each person is dropping off a quarter. All right, you just might as well count on losing that much. And then, that's the long run average. If we have a whole bunch of people play this game over and over and over, at the end of the night, we would expect to get an average of about negative 0.26. You've lost. Okay. Questions about that? All right, well, let's see about part B. Okay, it says if you bet $5 on the pass line in the dice game of craps, the probability of losing is 251 over 495, and the probability of winning, it should say, is 244 over 495. The prize for winning is $10. Okay, find the expected value if you bet $5 on the pass line. Okay, I'm not sure what all of that means, but I think I can find the mean. or the expected value. Okay, we get x, p of x. Okay, this time our values will be what? Okay, you bet $5 so you can get -5. Okay, and then the prize for winning is $10, but you paid $5 to play, so it's +5. Okay, probability of losing 251 over 495. And the probability of winning is 244 over 495. By the way, we should note that the sum of our probabilities is 1. Okay? All right, so that this is a valid probability distribution. So our expected value is 5 times 244 over 495. Okay, minus 5 times 251 over 495. I got minus 0.07. Okay. All right, very good. Minus 0.07. Okay. So, which is better? A $5 bet on the number 7 in roulette or a $5 bet on the pass line in the dice game? Okay, we got different opinions. That basically, yeah. I mean, in this case, it's our earnings, which is negative. So here we lost 7 cents. In the previous game, we lost 26 cents. So which one would be better to play? Individually, yes, but when we talk about long run average, okay, and that's a good point. One thing we'll be moving towards as we go, especially when we get into the next chapter, is when it comes to calculating probabilities, it's better for us to look at probabilities involving several things where we've averaged it together instead of just one trial. So based on the expected value, the long run average, we would say that this second game of craps on the pass line, is a better game to play. Okay? Okay, we got several other things here. Oh, let's look at this one about the life insurance. Very good one. It says there is a 0.9968 probability that a randomly selected 50-year-old female lives through the year. A Fidelity Life Insurance Company charges $226 for ensuring that the female will live through the year. If she does not survive the year, the policy pays out $50,000 as a death benefit. Okay, from the perspective of the 50-year-old female, let me tell you why it says that. Depending on which side of the table you're on, you're getting a loss or a gain. Okay, so we could do it from the perspective of the insurance company, or we could do it from the perspective of the person that they're selling this policy to. Okay, so we're looking at it from her perspective. What are the values corresponding to the two events of surviving the year and not surviving the year? Okay, if she survives the year, what's happened with her as far as her money? She just paid out $226. So we would say surviving the year is negative $226. Okay? However, if she doesn't survive the year, then somebody gets $50,000 minus $226. So I got $49,774. And I'm not sure why I put a parenthesis there. So let's just erase that. Okay. All right, so those are the two values. Okay. If a 50-year-old female purchases the policy, what is her expected value? And so given probabilities associated with each of these, we can say the expected value is, okay, she lives through the year, so that's negative 226 times the probability that she makes it through the year, which is what? Okay, 0.9968. Okay, plus she doesn't make it through the year. So that's when we get the payout. And the probability that she doesn't make it is going to be what? 1 minus the 0.9968, which I get 0.0032. Okay, so that's times 49774. Okay, plus 226 negative times 0.9968. I got negative 66. Is that what you all got? Okay. So if we lined up 1,050-year-old women that purchased this policy, okay, and then at the end of the year we assessed, you know, each of them is going to do one or the other. These are the outcomes. They either lose 226 or somebody gets this, okay? But when we average those things together, we would expect that the average benefit would be a loss of $66 per person. Okay? Questions about that? Okay, very good. Which means basically that the insurance company is doing what? Making about $66 per person. Okay? All right, can the insurance company expect to make a profit from such policies? We would say what? Yes. Okay, yes they can, because the customer is averaging a loss. Very good. All right, that's about all I really want to say about expected value. We may or may not have some time to talk about